Hi, everybody. This is Mr. Polly, and happy Super Bowl. Ooh, can you believe that the Chiefs won? Well, I don't know if they won or not. It is 4-16, but my dog picked the treat that said the Chiefs won, so I'm going to go with that because my dog's my friend. If you're looking at Le Chatelier's principle, which is what this is about, what we're going to use to explain almost everything is comparing Q and K. If Q is bigger than K, that means you have too many products, and it will shift to the reactant side. Shift to the left-hand side. If Q is, less than K, again, products over reactants, that means I have too many reactants. It'll shift to the product side. That will shift to the right-hand side. And what you do is you say on both of these, my favorite reason of all, algebraically. Okay? Any equilibrium system, when a change is made to a temperature, pressure, volume of gas, or concentration, there's a change in the position of equilibrium so as to oppose that change, which means it will shift to reach equilibrium again. Okay? It may not have the exact same numbers, but it'll have the same ratio. Remember, equilibrium is a ratio of products over reactants, and it's when the rate of the forward equals the rate of the reverse. The rate of one reaction will speed up or slow down while the other one is unchanged. Adding a solid, now there's one exception to that. Temperature, they both change, but endo changes more. Okay. Adding a solid and remember they both speed up, but that would be it. Instead of change, I should say they both speed up, but endo speeds up more. Adding a solid or liquid has no effect on as the rates are not affected. This is because concentrations are not changed, because we're talking about rates, so it's a concentration, it's a collision per unit time, and you can't do it faster with a solid or slower than a solid. We talked about a salt lick, a big salt lick, and a small salt lick. Taste the same level of saltiness. Adding a noble gas has no effect as the particle volume is essentially zero, and the effects on other pressures is zero. It does change the pressure of that noble gas, but we don't care. It's not doing anything. Only changing temperature can change K or a catalyst. I got burned on that one before. But a catalyst, which you almost never see, but only changing temperature can change K as far as these things go. All right, so you change the reaction to do that too. So let's look at this. We're going to look at the manufacture of ammonia. So if I decrease the volume, what's going to happen is I go from a big old box. Whoa, that's not a box. I go from a big old box to a little old box. Okay. Now, if you think about this, the reactants have 4 moles and the products have 2. So whenever you decrease the volume or increase the pressure, that does the same thing. What you need to know is it will shift toward fewer moles. Not any moles of gas. Okay. So more collisions between 4 moles compared to 2, so the reaction will shift to the right. Okay. The other way you can look at it is the concentrations change, right? So if you change, oops, that one jumped. I didn't think it would jump. The concentrations change because if I divide everything by 2, say I cut it in half, then that changes the concentrations because it's moles per liter. If I increase in temperature, in this case, I forgot to do this. This is negative 92, so I put my heat on the right-hand side. So if I increase the temperature, we know all the particles move faster, there'll be more collisions, the rates go faster, but the backward reaction is endothermic, so it removes heat, I'm going to say faster, by shifting to the left-hand side when the reverse reaction goes faster. Okay, so we're talking about this balance. So if you increase the temperature, it will always shift away from heat. Whoops, that's away. I'm not speaking with an accent. Away from heat. Okay, so I know it's going to be away, but why? It removes the heat better. Removes heat. Okay, increasing the concentration of nitrogen and hydrogen. So again, nitrogen and hydrogen are reactants. So if I have products over reactants, Do you see how if I add reactants, if that number goes up, right, Q will go down. So Q is less than K, right? If Q is less than K, it will shift to the right-hand side. Why? Algebraically, and that's a great way to explain it. You can say there's more collisions on the left-hand side, so more successful collisions and forward reaction rate increases, but my goodness gracious, and that will work. You can either talk collisions, but many times they want you to talk about K, okay, and it will specifically say that. Increase in concentration of ammonia. Well, ammonia is a product, right? So if I increase the product, then my Q is going to get bigger. And if Q is bigger than K, it will shift to the left-hand side. Why? Algebraically, okay? Or you can say more collisions on the right-hand side compared to the collisions on the left-hand side. So there's more successful collisions on the right-hand side compared to the left-hand side. So the reverse rate increases. I like it much better to say Q is bigger than K. So algebraically, it shifts left. All right. Oxidation of ammonia and the manufacture of nitric acid. I got another negative delta H, so I'm going to put plus heat. I'm just going to put the word heat this time on the right-hand side. I'm going to increase the pressure by reducing the volume. So my first thought is going to shift to the side with fewer moles of gas. Okay, so this side has 9 moles of gas. 4 and 5 is 9. This side has 4 and 6, which is 10. So it shifts to the left-hand side because more collisions for 10 moles of gas versus 9 moles, so the reverse reaction speeds up more, and that works. If I increase in temperature, remember it's going to shift away from heat. It's going to shift to the left-hand side. Backward reaction is endothermic, so removing heat speeds up the reverse reaction more. Increase the concentration of ammonia and oxygen. Ammonia and oxygen are reactants, so products over reactants. If this gets bigger, Q gets smaller, so Q is less than K, shifts to the right-hand side algebraically. Uh-oh. All right. Increase in concentration of nitrogen monoxide in water. Those are products, so products over reactants. If I increase my products, then Q is going to be bigger. Q is bigger than K, so it'll shift to the left-hand side. Why? Algebraically. Okay. All right. Summarizing the shift. So remember, when you explain it, you have to explain it with Q or K or the number of collisions. But here's how we can remember it. If you add an aqueous or gaseous reactant or product, it'll always shift away from the add. Okay. The side added's reaction speeds up due to the increased concentration and increased collisions. And again, remember I have products over reactants. Q is less than K, algebraically. Reduce volume affects only gases. It'll shift to the side with fewer gases. Or no shift. Remember, it could be no shift at all. How could it be no shift? If there's no gases, or if there's equal gases. All right. So relative increase in collisions is greater on the side with more gases. So reaction shifts towards the side with fewer gases. Increase in pressure. It's the exact same thing as reducing volume. Okay. Remove aqueous or gaseous reactant or product. This is important. This is done by side reactions, often precipitation. We think this can't happen. It's weird to think of pulling something out, right? But you can remove them. Shifts towards the side removed that has fewer collisions. So fewer collisions and the rate of leaving that side. Okay, so let's go back to it. It's going to look at what happens to Q. So Q changes. And we keep saying if Q goes up, then I have too many and it'll shift to the left-hand side. And if Q goes down, all right, I have too many products. Too many. If Q goes up, this is why I always write, you see me, I always write P over R. Right? So if Q goes up, I have too many products, so it will shift to the reactant side. So it'll shift to the left-hand side. And if Q goes down, I'll have too many reactants, and it will shift to the right-hand side. So right-hand side. And of course, our reason is our old friend, algebra. Add or remove a solid or liquid, no effect. The number of collisions per time is not changed. Adding a noble gas, no effect. Gas particles are so small they don't change the volume. So really, they're so small you don't even notice them. Okay? Noble gases won't react, so the particles and rates are unaffected. Add some weird things that are not a noble gas. So if it adds something that's not a noble gas, it will react or add something. Okay? If it reacts with something, it will remove that thing. Adding excess concentrated NH3 will precipitate Ag positive and remove Ag positive. Look for acids to change a -2 ion into a -1 ion that removes it. So that seems weird. So if I have carbonate and I add H positive, what that means is carbonate will react with H positive and it will turn into HCO3 negative. Well, HCO3 negative is not the same thing. Okay, that would be an example of that. If you, let's see here, look for acids or bases to be a source of added H positive or OH negative. So if my equilibrium is H positive plus NO2 negative, it yields HNO2, and I add like HCl. HCl is a source of H positive, so I'm really adding H positive, which will shift it to the right-hand side. If I add heat, it will shift away from heat in the reaction. Both reactions speed up, but the endothermic reaction speeds up more. All right, that's what people forget. They just think it happens to one, but it does to both. Whoa, my screen just went silly. Okay, optimum conditions. AP asks for optimum conditions or maximizing yield. So how do we get the most product? So product is on the right-hand side. So this means what can I do to make it shift right? That's it. So if I wanted to shift to the right-hand side, I would, okay, so let's look at pressure. Remember, a very high pressure. So if I have a very high pressure, it shifts towards the side with fewer moles of gas. So this side has 4 moles of gas, this side has 2. So increasing pressure shifts it to the right. A very low temperature that removes heat, that will shift it to the right. If I remove a product, it affects K, shifts it to the right. If I add reactants, it'll shift it to the right. That's it. And under 15, how glorious. Toodles.